Hi everybody, today we're talking about trig derivatives. So the first thing we're going to do is just start with y equals sine x and ask the question, what is the derivative of y equals sine x? And just from visual inspection we can do this. I see values here where the slope is going to be 0. Every time I have a turning point here, I'm going to have a derivative of 0, slope of 0. So I'm going to go ahead and mark those points as 0. And just from visual inspection here, if I'm looking at this graph of y equals sine x right at the origin, it looks like that has a slope of 1. It's really, really close to it. It's definitely a positive value, and if you zoom in there, like it looks like we go over 1, up 1, and all those little boxes. So my derivative, let's use a different color, my derivative should look something like a value of 1, and then a value of 0, and then a value of -1, and then a value, oops, let me try that again. I'm going to try and get that more accurate for us. Value of 1, a value of 0, then a value of -1, then a value of 0, then a value of 1, then a value of 0, then a value of -1. Well, that looks awfully familiar. This particular graph that I've drawn there in green reminds me of another curve that I know, y equals cosine x, and it is indeed true that the derivative of sine x is exactly cosine x. See how perfectly they line up? So if we're keeping track here of what the derivatives are, the derivative of sine x is just going to be cosine x, just like that. Bam. And now you might be thinking, well, that means the derivative of cosine is sine. Let's check it out. It starts okay, like the derivative of this point is going to be 0, the derivative of this point over here is going to be 0, the derivative of this point is going to be 0, the derivative of this point is going to be 0. But I notice here that like this slope right there, that's about -1, not +1. The slope of +1 comes over here, right? And then the slope of -1 again down here. If I graph those points, I actually get not positive sine, but it looks like the sine curve just got flipped upside down. It's negative sine. This checks out because one thing we know about cofunctions, a function whose first name is co-something, like cosine, cotangent, cosecant, they always start going downhill. And if the derivative measures the slope, which it does, then a slope going downhill, a curve going downhill, means that the slope will be negative. So it's not a surprise to me that cosine, co-anything, the first name of that derivative is going to be negative. So there we got our first two derivatives. If f of x is sine x, f prime is cosine. If f is cosine, f prime is negative sine. Based on just those two derivatives, we're going to be able to get all the rest of these guys. Okay, we're not going to look at the graphs anymore. We're actually going to use some trig knowledge we have. For example, tangent x, we know, is a quotient function. It is defined as sine divided by cosine. It's defined a lot of different ways too, but this is a fact, right? This is a quotient identity that tangent x is sine x over cosine x. We're going to use that to our advantage, plus the quotient rule. We know how to find derivatives of quotients in calculus, right? If I asked you for the derivative of, we usually say u over v, that's going to be u prime v minus uv prime over v squared. Here my u is sine and my v is cosine. I'm going to just apply the quotient rule here, and let's get a derivative. The derivative of tangent x, therefore, is u prime, derivative of sine, cosine, times v, which is also cosine, minus, oops, I'm going to need to move this. Can I move it? Nope, I can't move it. I'm just going to start over down here a little bit. Sorry about that. I was hoping I could just move that down. This gives you plenty of time to be thinking about what we're going to do for the v prime u and that kind of thing. Okay, so the derivative of tangent x equals u prime v, so cosine times cosine, minus u, which is sine, times v prime, which is negative sine. Okay, so that's times negative sine x, all over v squared, cosine x, and I'm going to put that in parentheses and square it. Quick side note on notation here. You probably know this, but maybe not. If I write cosine x squared, this is a really vague term, right? If I have no parentheses on there anywhere, I've got that squared hanging on the x. Do I mean take x and square it and then take the cosine? Or do I mean take the cosine of x and then square that number? It's really confusing. So we've got some different things we do for notation here. And the rule of thumb is unless you put the cosine x in parentheses, then you don't mean to square it unless you put the square on the cosine. So these two expressions that I've just written here mean the same thing. And that square on the cosine is kind of a shortcut or a shorthand so that we do not have to write the parentheses every time. Okay. So we're going to go back here and we're going to rewrite this a little bit. I'm not doing any more calculus, I'm just going to do some algebra here. So this turns into cosine squared, and I know that negative times negative is positive, so cosine squared plus sine squared divided by cosine squared. Okay, and you remember from pre-calc or algebra 2, whenever you learned this, sine squared plus cosine squared is 1. I will be happy to show you why that trig identity holds true at any time if you would like me to, just not right now because we're focused on the derivatives. And now 1 over cosine is another name for secant, so the most common way we look at this derivative is as secant squared. The derivative of tangent is secant squared. Fantastic. Okay, so now you got 3 things to memorize. You're going to get 3 more to memorize. But notice kind of a pattern here, right? Sine and cosine belong together. I will let it as a challenge or a learning opportunity to you to do what I just did with tangent. You do that with cotangent sometime, okay? Take the time. Your teacher might make that actually an assignment for you to actually develop the derivative of cotangent using the quotient rule and the fact that cotangent is cosine divided by sine. Okay. And you will see when we get that it will be negative, not a surprise. Cofunction has a negative derivative because cofunctions go downhill. Negative cosecant squared x. Fantastic. Okay. Graphically, we can actually see this pretty easily. I hope you can see. If I graph this, hopefully you can see it. Okay. Tangent x. So tangent x has a slope that is always positive. It is never less than 1. The flattest this thing ever gets is right at the origin when its slope is 1. And it has asymptotes. The derivative, the slope, goes to infinity at every multiple of pi halves. So when I graph secant, all right, I have this property pretty much, right? Secant is never less than 1 or greater than -1, so the minimum value of secant is 1. We know its asymptotes are at pi halves and negative pi halves. It has the same asymptotes as tangent because both secant and tangent have cosine in the denominator in their definitions, so they will have vertical asymptotes at the same angles. And the slope goes to infinity of tangent. That red line gets steeper and steeper and steeper every time the blue line goes up to infinity. If I make this squared, it's going to accomplish multiple things, but not the least of which is that now all of those little U-shaped pieces of this graph are above the x-axis, meaning the values of the derivative, secant squared, is always positive. Fantastic. Okay. Last one is secant. Well, secant and cosecant, but you see now that these things have buddies. They kind of come in pairs. So while it looks like you're going to have 6 things to memorize, you really only have 3 things to memorize, and then recognize like this positive negative function cofunction pair thing that happens. All right, secant. Secant x is 1 over cosine x, and without any chain rule, we don't know the chain rule yet, probably when you're learning this, so we're going to use the quotient rule again, and the derivative of secant, d dx secant x, is going to be u prime, the derivative of 1 is 0, so that's convenient, times v, which would be cosine, minus u, which is 1, times the derivative of cosine, which is negative sine x. Okay, so it's going to turn into a plus here in a second, over v squared. So that first term goes away, and we just get positive sine x divided by cosine squared x. There are a bazillion ways that I could simplify that. The way we typically choose to simplify this expression is by splitting it up as 1 over cosine times sine over cosine. 1 over cosine is another name for secant. and sine over cosine is another name for tangent, and we get secant times tangent. That's just kind of like the most common way this is simplified. Secant x times tangent x, and then cosecant will be negative cosecant x times cotangent x. I know my handwriting's kind of sloppy here, but I'm sure you can find a chart that has those things written a little bit more nicely if you look online. That chart is something that you need to commit to memory. An ounce of understanding is worth a pound of memory. So if you understand where they come from, if you remember that cofunctions always move downhill, which means their derivatives will always be negative, that will help you out. And remembering that tangent and secant have the same denominators, meaning they have the same vertical asymptotes. Cotangent, cosecant, same denominators, same vertical asymptotes. This hopefully is just more fuel on the fire of understanding why secant is 1 over cosine instead of 1 over sine. A lot of times elementary trigonometry students, like when you're in geometry or algebra 2 or something, and you're learning about these functions the first time, you're like, secant goes with cosine. Well, that's dumb. I feel like secant should go with sine. But this makes sense. It's not that secant should belong with sine, but that secant should belong with tangent. And then cosecant and cotangent, those co-functions belong together. This is one more reason why tangent and secant belong together. All right, that's it for this video. I hope this is helpful in knowing the trig derivatives, and then you can apply them using your other derivative rules.